Neste momento, daremos continuidade às atividades do segundo Fórum Mundial de Dislexia, convidando para se dirigir à mesa a professora Marialuisa Navas, que coordenará os trabalhos desta manhã.
Bom dia. Primeiro em português e depois eu vou mudar para inglês. I'll just say a few words in Portuguese and then I'll switch to English, okay? Sejam todos bem-vindos a esse último dia do Fórum. Para mim é uma grande honra estar aqui coordenando essa atividade e, mais do que isso, vou usar essa oportunidade de agradecer a Ângela e toda a equipe por fazer parte desse fórum e por ter me convidado para participar não só da programação científica, mas também de ajudar na organização desde o início. So I'm thanking Angela for inviting me and to be part of this very selective group of speakers and organizing this forum, which is already a success, and I'm very happy to be able to participate in this special activity, introducing the speakers for today, for this morning. So this session here today is going to talk about the technology helping children to learn to read and write. And it's my pleasure to ask Marialuisa Martelli from Italy, who is going to talk about procedures, innovative procedures for different linguistics contexts in reading and writing. Thank you, Marialuisa.
Thank you very much for inviting me. It's been a pleasure being here, and it's a very, very interesting conference. Thank you. Okay. So I work at La Sapienza, University of Rome, and at Fondazione Santa Lucia. I work on brain damaged patients and with children with developmental dyslexia. I'm a visual psychophysicist, so what I'll be talking about may appear slightly, is it too loud? May appear slightly different relative to what we have been hearing up till now. So I'm going to talk about, in the context of developmental dyslexia, I'm going to talk about how to shape procedure to help children to learn to read on the basis of what we have done in research. And so procedure may be, well, from what we have learned in these 2 days, these procedures, which sometimes are also old procedure, may be indeed innovative. So to frame my talk within the context of what we have heard, what I'll be talking about is the decoding process. So here is the model that Joan Ziegler presented in the first day of this conference, and my talk will be concerned with decoding and the availability for letters, and how these, we'll see that these can impact the whole chain of the process. Now, there are models about this part of the system that I'm not going to talk about, though. So Of course, dyslexic children are not a uniform group. There are different subtypes. It is interesting also to see at the qualitative errors they make that are indicative of the different subtypes of dyslexia. This was already thought by Fairbanks back in 1937, where he noticed, looking at eye movements and type of error recordings, he noticed that when a poor reader hesitates, that indicates that he has to regress to move their eyes back to a word that is difficult to decode. Thus, these type of errors seems to be related to decoding. Now, this is all interesting, but we are not going to talk about accuracy. I'm going to focus on speed measures. And I'm going to focus on a particular language, which is Italian, because these are the majority of the data we have, and is a shallow orthography language. It's very regular, and it has some typical characteristics. Here I'm showing, so forget about the lower graphs. The upper graph, look at the empty symbol. Those are the mean speed on the left and accuracy on the right as a function of grade from first grade up till 8th grade. So as you see on the left, reading speed improves. It improves with a particular law, which is a power law, and which is worth to study, because it's indicative on what actually children are learning during this learning phase, and it continues improving. On the right, you see accuracy. Now, this is a particular feature of shallow orthography. So accuracy reaches perfect performance very early, no? Within the first 3 years of schooling. Thus, when you look at dyslexic children in shallow orthography, their main problem is to speed up reading. Once the orthographic grapheme conversion rules are acquired. A particular feature of a marker of their deficit is the word length effect, meaning that we are slower as a function of how long is the word. So this is also true for normal reading. So on the left, you see vocal reaction time. So it's the onset at the pronunciation as a function of word length in terms of number of letters. And 4 different grades. Here I'm showing only 6, 7, and 8. I need glasses. Grade and adults. And as you see, what happens is that improving age, with age, vocal reaction time decreases, so all the function goes down. And there is a large difference still from 8th grade to adulthood, okay? So the diamond compared to the X's. However, there is another interesting phenomenon that occurs here, which has been mentioned yesterday by Dehan very nicely, that there is a range in which vocal reaction times are substantially independent of word length. And this range increases, meaning that children are able to process longer word at no cost as a function of grade level. And on the right, you see dyslexic children. These are 8th grade dyslexic. And you can see that, first of all, looking at the numbers on the vertical scale, you see that they are extremely slow. So the 2 scales are very different. Second, you can see that vocal reaction time increases with length, with a large proportionality, and that they don't show these parallelly processing of short words. So they, going from 3-letter words to 4-letter words, they already show a strong length effect. I must mention here, and I will not mention it later, our definition for the dyslexic groups in the data that I'm going to show you. We typically do some functional reading tests, and they are pathological inaccuracy or speed. And to say that they are in the dyslexic groups, they are 2 standard deviations below the mean. Then we also administer some word and non-word list test, and they must fail also in those relative to controls. I'm going to give you a trailer of what I'm going to talk about. So we conjecture that the pre-lexical aspect of reading play a relevant role in developmental dyslexia, that dyslexic children have decoding problems due to integration failure. Now, of course, there is the whole story of subgroups that I'm not going into now. So our evidence suggests that in order to optimize decoding and rehabilitation program for rehabilitation program for dyslexia should, first of all, start large. Start with large print sizes, then start short, so short words, not bigram, because probably we have access to rehabilitation of these children when they are already in their 2nd, 3rd grade, so they should have acquired grapheme to phoneme conversion, but of course that is part of the training if they didn't. Third, present stimuli tachistoscopically or within an RSVP streaming, rapid visual serial presentation. We'll see what it is. Now, I could end here, but of course I need to show why this type of procedure is useful for the child. So this will take a little long, so be prepared. And I'm going to start to details. No, I'm not going to start to details. I'm going to start with the big picture, sorry. So we are going to propose that there is an integration failure. So anytime we propose a possible mechanism as responsible or co-responsible with other mechanisms for a particular pathology, we need to address 3 main concerns. Reliability, so the fact that actually you can measure the deficit in these children, the fact that the proposed solution is can plausibly and explicitly explain the reading deficit, because at times perturbation have been proposed that then did not survive the demonstration of plausibility, and then selectivity. So why do these children have a deficit that pertains a selective behavior and not other cognitive functioning? Now, if we translate this into our hypothesis, so when I talk about integration, I talk about crowding. So you already have heard about crowding 2 or 3 times during this conference by some colleague, and I'm going to talk a lot about it. So I'm going to explain to you what crowding is. So if our hypothesis holds, we need to be able to answer these 3 questions. So do children with dyslexia have marked visual crowding? And how can enhanced crowding impair reading? And also, is the reading behavior these children show consistent with a crowding impairment? And also, why and how can we predict the selectivity for words and reading due to the integration failure? Now, what is crowding? Okay, look, I'll give you a small demonstration. So look at the green plus, And while looking at the green plus, you need to identify the letter on the left. What letter is it? A. It's easy, okay? So that size does not hit our acuity limit, so it's large enough for us to see it far there, okay? Now, keep your eyes on the green plus and try to identify the letter. It's impossible, okay? So you know an A is there, but you cannot identify it. Okay, now, in order to identify it, you need to move your eyes from the red minus to the green plus. If you try that, now you see that you identify the letter again. What happened? You see these, I don't know if the small one is visible, but there are some circles around the demo. They correspond to the region in the visual field in which we integrate the visual information that falls within, okay? So when we are on the plus, the region is a small circle. That small circle is small enough to isolate the letter A, okay? So you identify it. When your eyes fixate on the red minus, the circle is the red one, the large one. That circle is too large to isolate the letter A, and it compulsory averages all what's inside. Now, there are models on what happens inside that region, but I'm not talking about it. You need to know, though, that there are these integration fields, and you may think about them as perceptual second-order field, and all what's inside is combined. All what's outside is excluded. Okay, this is a demonstration that is important for me to introduce a concept that is threshold, that I will use later, and to show you a particular feature of this integration failure. So let me introduce threshold. So you see a bunch of letters on the right. Now, one is in the middle and two are the flankers around it. Now, if we look at the flankers, contrast increases going from top to bottom, meaning the difference in brightness between the letter and the background increases, okay? Threshold is typically defined as the minimum difference in intensity, in this case contrast, needed to achieve a certain percent correct. Thresholds are very important for this talk what I do, because they enables you to compare different observers of different age, of different skills, dyslexic and control, at the same level of task performance. This means that the task at threshold is equally difficult for all observers, okay? So you are looking at the pure effect of intensity. Okay, now let's go to the demo, to the real demo. So your task is to move your eyes up and down on the little square and try to identify the central letter. You'll see that at the top is easy, and at a certain point it becomes difficult, like at the third, fourth row for me. What happens? So before the row in which it becomes difficult for you, letters, the flanking letters, the letters surrounding it, are visible. So you can say that they are there, but you cannot quite tell what they are. As soon as you can tell what they are, now you fail identifying the central letter. What does this mean? It means that this phenomenon does not occur at an early stage of processing. It occurs later. It's not... if we think about a hierarchy, which has been shown yesterday by Highness in a better way, we can think about perception as going from feature, perception in this case in word recognition, from feature to words, okay? So, oops, no. So, feature, you can think of a feature as a simple oriented line. Then we have letters, and then we have word. Masking phenomena affects early stage of processing, how we detect features and single letters, while crowding impairs word recognition, so letters integration. And, okay. So it occurs at a later stage. How do we measure crowding? So typically you measure critical spacing, the distance between the target letter and the flanking letter in order to achieve a certain criterion level of task performance, that a threshold, as a function of the letter eccentricity. So, and what you find is a nice proportionality. This graph maps the integration field across your visual field. The plus, the gray plus represent the fovea, where you are looking at, okay? And these ellipses are data. So our critical spacing ranges as a function of where you have to do the task in the periphery, okay? Going from the fovea, maybe I should use this. Going from the fovea to the periphery, you see that the size of this field increases, okay? And increases with a certain proportionality, which is equal to half of the distance from the fovea, okay? So if you are at 10 degrees of eccentricity, the size of this field are 5 degrees. A degree is like your fingernail at an arm length distance. Okay, that's about the size of 1 degree. So they are large, they are huge. The fact that they are huge, they enable people to look at what happens inside, okay, using the periphery. But we also have them in the fovea. So this tells us that in order to do the task, remember we are at a threshold, in the visual field we have integration field of all sizes, but the smallest one we can use to isolate the object has a size that scales with eccentricity, and at times is too large. So most of the time, in our everyday life, most of the objects are in that range, okay? They are outside of where we are looking at. I'm looking at this room, and most of you are in my periphery. And my integration field are too large to identify, for example, or see your faces, okay? Because they are combined together, okay? So most of the time, most of the word is crowded. Okay, now this is a long introduction that I'm almost done. Crowding, this is also true for reading. So if you look, this is another demo. If you look at the plus in the middle, and you try to see if the line of text above and below are different, you'll see that they look alike. So, however, if you actually move your eyes on the line of text, you see that not only they are not alike, but the bottom one doesn't even contain letter. Okay, so if you have, this is also to connect to what have been said earlier, if you have failure of integration, you have several phenomena, okay? So failure of integration can explain many features. Failure to read, you cannot read. You have a word length effect, because as words become longer, they go farther in the periphery and they are more subjected to crowding. Letter position uncertainty, because a feature of crowding is position uncertainty. And this is interesting because, and it also connects with interaction with languages. So there is a very interesting paper by Frost in which he actually looked at letter position flexibility across languages, in particular the sensitivity, so the absence of letter position flexibility in Hebrew, for example. And there are other phenomena like letter confusability, visual span, number of letters that you can parallelly process, superiority effect, etc. While single letter recognition is spared. Okay, so let's recall that to measure crowding, you measure critical spacing, the distance between the letters needed to achieve threshold. One important aspect as a function of eccentricity. One important aspect is that, and you do this, sorry, as a function of size. One important aspect is that the relevant spacing is not the empty space between the letter, but the center-to-center distance between the letter. This has important implication. So crowding doesn't care about the empty space. It cares about the center-to-center distance. This means that it is independent of size. Now, crowding affects object recognition, affects letter recognition, but also words. So we think that, okay, we have words are hyper-learned, so we must bypass this bottleneck. However, we showed that crowding affects words and face recognition equally, as shown in the lower graphs. So you see critical spacing as a function of eccentricity, and you see that all the data falls on the same law in which critical spacing enlarges as a function of eccentricity with a proportionality of around, in this case, 0.3, a little lower than the expected by BOMA. And it is independent of size, as I told you. This is a marker of crowding, okay? So crowding impairs words as well as letters, as letter string. So where it happens, there are some studies with brain imaging techniques that try to locate the areas that are susceptible to crowding, and they are not many, and a relevant one, I think, is this one from 2012, in which you see a modulation on the ventral pathway. We also are looking at the activity in the word form area relative to crowding. Okay, so if our theory for dyslexia, now you know crowding, okay? Now let's see what this has to do with dyslexia. So if we think that dyslexia is failure to integrate, then we need to make sure that the first levels are spared, so identification and detection. So we did that. We measured contrast threshold on a blank field and in noise. This is visual noise. This is relevant because a difference in the pattern between these two conditions would indicate a presence of internal noise in the observer, which is a low thing, a low-level stuff that we don't want, and we don't get it. And we find that dyslectic and controls are equivalent in the terms of their contrast threshold for identifying single letters, both on a blank field and in white noise. And however, they are very different when they have to identify long words, okay? This is a matching task, so the words are always the same. It's a set of 10 words, so it's potentially very easy, okay? They don't need to read, they need to do a matching task, and they are unable to do it. They become able to do it when you give them enough time. What does it mean? Well, we'll see that with that more time, they can move their eyes on the on the word, and now they become like controls. Okay, but this is a problem, because the problem of dyslexia is slow reading. So now let's see integration. So do children with dyslexia have marked visual crowding effects? So the first thing we do is we look if they have abnormal isolation or integration field. They have been called in the two ways. So this shows critical spacing as a function of eccentricity for controls and dyslectics. And as you see, in average, dyslectic children show sizes of isolation fields that are larger than control. So, and this effect that is shown here as the average of the groups is independent of size. So, what this means for training them is that size and not spacing is a relevant dimension to enlarge in order to facilitate them, because increasing spacing breaks the gestalt of the word, okay? Breaks the good shape of the word, and there are reasons for that. While increasing size prevents the letters to be teared apart. However, it has exactly the same effect. So now, they have abnormal crowding, but does this have anything to do with the reading rate? Okay? Is the reading rate limited by the size of this larger isolation field? So we studied that measuring RSVP, as you can see here. In the RSVP procedure, a series of words are flashed at the same retinal location, and the observer can read the words with unlimited time, so pronunciation does not play a role in reading rate threshold measured with RSVP, as well as eye movements. So you speed up and you slow down it's very slow. You speed up and you slow down the sequence, and you find the word duration needed to achieve a certain criterion level of task performance. And you get these nice curves in which reading rate improves till a certain point and then flattens out, okay? So there is a cliff and a plateau. These break point is directly proportional, the point, so the size at which you get this break point, it has to do with the critical spacing in the fovea. There are theories for the plateau that I will explain in a moment. If you do this with so this shows the same curve as a function of eccentricity, how it changes. And people, the group of LAG has a long series of paper in which they try to explain this curve with visual span. And visual span is measured with letter triplets as a function of the retinal position, and it indicates how many letter positions you can process in parallel. And they find a nice relation between visual span and reading rate. However, visual span is actually crowding, okay? So they are not different things. So the number of letters you can parallelly process is directly proportional to the characteristics of crowding. We don't work through it, but you can work. This is Bowman's law, so the proportionality I've talked about to you. So the eccentricity function, and this is a Legge's conjecture about visual span. You can work out the geometry, and you find out the geometry of crowding, because as word becomes longer, they go more in the periphery, so it's not only foveal crowding that counts, but it's also how it increases as a function of eccentricity. You work out the geometry, and you nicely predict all those curves, okay? Just with crowding, okay? So crowding explains how reading rate improves with size. And here I am showing our dyslectic data, which are the solid line, which is the same graph as before. And these are the controls. So the controls in the periphery. So as you see, the breakpoint of this curve is equal. So dyslectics and controls have the same breakpoint. However, controls are tested in the periphery, okay, while dyslexic are in the fovea. So a dyslectics is like a control. Reading rate for a dyslectic at this breakpoint is equal to that of the control if the control is tested in the periphery. Now, you also see that dyslectics still are slower than controls when you reach maximum reading rate, okay, which is also shown here by the fact that all the points are below this line. More in general, maximum reading rate obtained is related to the amount of crowding that is shown on the horizontal axis. The more the crowding, so the larger the isolation field, the lower the rate. The smaller, the higher. Okay, so this is, if you are reading a text, most of the stuff that you are looking at is in the periphery. Some of it is in the fovea. This is your window of visibility over the text. But if you are a dyslectic, your window is much smaller. Thus, you need to move your eyes across the text in order to get the word, and this is costly. Okay, it's time-consuming. This graph shows the same thing I've shown you before, but pulling together different studies. And you see that normal controls fall nicely this low, and dyslexic fall way below. This is not new. So Spinelli et al. Already found that increasing spacing between letters improves vocal reaction times for dyslectics, but not for control. Bohm, back in 1977, showed that dyslectics have, for letter triplets, have larger crowding than controls, but note the fact that also children have larger crowding than adults. Thus, there is a developmental trend here that follow reading acquisition. Also, Atkinson tested crowding in the fovea, though. And crowding improves, but it has a long-range improvement. So I'll show you some of these. Of course, for timing reason, we cannot show everything. So is a reading behavior compatible with the crowding hypothesis? So the pattern of eye movement is, so you see a dyslectic children, you see it makes many fixation. So to have in the fovea the relevant part to the code, while the control makes much fewer fixation. I already told you about the visual, the number of letters that can be processed in parallel. These are our dyslectics. Now I'm showing you the dyslectic divided in two subgroups. So some of them do seem to develop a slightly larger parallelly processing for words, while others are deeply impaired by length. I think I'm going to skip this. No, I need to skip this. And so if they do have crowding and size is relevant, then one simple thing we can predict is that the viewing distance these children have should be shorter than the control, okay? Do they read at a closer distance than control? We tested that, so we measured speed as a function of character size, and we also measured distance as a function of character size, and these are new data. And what we get the function that I've shown you before for dyslectic and controls that show that this breakpoint is larger for dyslectics than controls. But most importantly, we find that this is a normal reader that is reading at his comfortable distance, and this is a dyslectic reader. And we find that the reading distance in centimeter here as a function of character size is different in the two groups. Dyslectic children approach the text so to have it larger in its retinal projection. And the relevant point are this one, because of course when the character size becomes much large, the length of your arm is not enough for estimate distance properly. So the relevant point are this one, where you can see a large difference in distance between controls and dyslexic. And this distance is with some noise predicted by the reading rate as a function of size at a fixed distance. So from that we can predict the actual distance with some noise, of course. Okay, so this is just a brief presentation on some data on rehabilitation training. So in this case, the rehabilitation training has been done using a 35 session and using tachistoscopic presentation, very rapid presentation of words, and the difficulty of the task is increased as soon as they reach a certain level of task performance, and it is increased by reducing presentation time and increasing the lexical components, so going from high frequency to low frequency, from short to long, okay? And these are some data about how performance change as a function of the treatment. Accuracy, you see an improvement in the treated children, and in accuracy, in speed, both with words and pseudo words, and you also see a nice improvement in vocal reaction time. So let me end up with the last thing. So why would a crowding deficit produce a selective reading disorder in the absence of impairment in other object recognition ability? So I told you that crowding impairs faces, words, etc., and everything is in the visual field. Why then these children have a reading impairment? Well, because when we read a text, reading a text is not like recognizing a face, it's much more like looking for Waldo in this panel. So a text is made up of little objects very close to each other. We need to decode them in a sequence, and we do it extremely fast. I mean, with our SVP reading, we can arrive at 1,000 words per minute. So decoding is fast. So we do this impressively well. Why I bet that you will never find Waldo here. A face is obviously much easier when we look at a face in the fovea, and thus these two aspects come together if we look at in the periphery, but we never recognize faces in the periphery. We always look at the face. So this is not something required, while when we read a text, we need to scan the text and plan the next arcade and move our eyes to it and do a pre-processing and process most of the stuff that we are fixating on. And the more we can process in parallel, the faster we'll be, and the bigger the chunk that will enter into the model that have been discussed in other talk. So these are the reason why. In order to optimize reading, you need to start large with large print sizes, not spacing, size. Start short, start with short words, and then increase the size. Present stimuli tachistoscopically, because the stuff that I didn't show you has to do with the selectivity for decoding of the deficit. So tachistoscopic presentation enables you to stress the decoding process, and then progress in small step, reducing exposure time, reducing size, increasing word length, and increasing lexical complexity. These are the people that have been involved in some of the study I showed you. Donatella Spinelli, Pierluigi Zoccolotti, Gloria Di Filippo, Maria De Luca, Dennis Pelli, and Fabrizio Zeri. Thank you.
Thank you, Marialuisa. We have time for one question.
Ok, vou levantar.
A quick
Dr.
one.
Martelli, very good presentations, congratulations. Quer que eu fale em português? É melhor, né? Ok. You know, very good presentation, very good. And I was just wondering... desculpe. Eu não estava usando o tradutor, então sintonizei na outra língua. Vamos lá. Muito bem. Quando a gente fala... Pegou aí?
Alô? Só vou pedir para que seja uma pergunta rápida para a gente não atrasar a próxima
Com certeza, mas
por
eu acho
favor.
que ela é muito pertinente, por isso que eu queria fazer.
Ok.
Tá?
Thank
Muito
you.
bem. Quando a gente fala em leitura, nós temos de lembrar que leitura é... Ok. Ok?
Yes, I will.
Ok. Quando fala em leitura, nós precisamos movimentar os olhos. Então, ok? E, então, o que é a leitura? A leitura é uma sequência de fixações, onde nós temos, então, o fenômeno do crowding, implicando o fenômeno do crowding, o fenômeno da excentricidade e da acuidade visual e do contraste. Mas, ao mesmo tempo, nós estaremos movimentando os olhos. E para movimentar e para calcular o próximo movimento sacádico, os micromovimentos sacádicos que compõem uma leitura, nós precisamos, então, também considerar a parte, então, da coordenação periférica que é feita pelos dois sistemas envolvidos na leitura. Então, eu queria perguntar para a senhora se estão sendo feitos alguns estudos e o que a senhora poderia nos dizer sobre também a confluência da participação do sistema parvo-celular, que é esse que a senhora conversa aqui, sobre a excentricidade e o crowding, com a parte do sistema magnocelular, que controla a movimentação esquerda para a direita. Porque nós sabemos que, nas crianças disléxicas, nós temos problemas com a oculomotricidade, com a conjugação do olhar, com a parte de fixação e também, se por cima disso tudo, ainda tivermos um problema de contraste, do threshold for alterado, e isso, inclusive, depende não só do tamanho da letra e tudo, mas também do nível de do nível de densidade do texto, como que a senhora vê todos esses fatores juntos aqui? Eu sei que é uma pergunta complexa, mas é importante que a gente entenda, porque senão a gente fica pensando que é só aumentar a letra e a criança vai ler melhor, e não é bem assim.
I'll say two things and then So, okay, it's a very complex question. It's a very complex question. So there is a huge literature on, because it tackles into different components, no? There is a huge literature on programming the next cascade, which is the pre-processing we do in the paraphobia. There is wonderful works by Rainer. So I know you are an ophthalmologist, because I heard. So I think that it is hard for me now to fully answer this question. So it may be better if we talk separately.
Yes,
Okay.
I would ask so. Thank you, Marialuisa.